In our previous videos, while we were discussing C++ object lifecycle, we created a sample class which simulated Java-like string in C++. Part of that exercise, we've added a lot of new features of C++ programming language and a lot of new syntax. So a lot of it was done very informally, just based on intuitive understanding of the topic. But now I would like to refocus our attention a little bit closer, focusing on features such as constructor initializer lists and the usage of const qualifiers, constant keyword, in different contexts of the programming language. So this is a second part or continuation of our C++ object lifecycle series. So this is the presentation that we're going to use today. And as we begin to discuss various topics in this handout, I would like to reopen our string project. Just open the version of the string project that we used in our prior presentation. And I'll just simply go to the source subfolder and drag and drop all of the source files that we were using prior to this. So this is our Java-like string, class name string, and so we can probably find a lot of elements presented in this handout already present in our sample application. So this pointer, of course, becomes available in every member function. So what is this pointer? There is a special keyword, this, that contains the address of an object for which member function was invoked. Member functions require an object to be called, and this pointer is that reason why we need an object. So for example, when we create string name hello, okay, and we use it in different places, where we want to find out what is the length of this string. So length is a member function. Right here, if we open our header file, so the length is the member function of our class string. And when we make a call into length, inside this length function, this pointer will be pointing to the object for which the function was invoked. So once again, when we run this function length, when it executes, it gets access to our object for which the length function was invoked. So for example, when we use other object named greeting, and if we were calling a length function of the greeting, then this pointer would be pointing to another object. Okay, so for whichever object the length function is invoked, this pointer inside every member function, like those that we have in our class, it will be pointing to the address of the object for which the function was invoked. And so this is how a member function knows literally what is the object for which it was invoked, so that it can get access to all the data member variables, like in this point. Now, if you really want to, if we have these two member variables inside x and y, inside the class name point, and adjust is a member function, then you can refer to mx and my by explicitly using the pointer to mx and pointer to my using this keyword, because this keyword will be populated with the address of an actual point object for which it was invoked. So that's the basic function of the this keyword. And sometimes you may want to return the this keyword, for example, in kind of similar context of our string sample here, if we had an append function which was trying to concatenate itself with another string, which is what we did with our concatenate. So concatenate right here was a very similar function to this append. But it would be possible to actually use a syntax to chain these appends, just like this. What it means that we can construct 3 different strings, populate these 3 different strings with different text, and then we could call string 1 append string 2. So the period or member access operator is associated left to right. So basically what it does, it proceeds to evaluate this part of this longer expression. So then this function append, if it returns back reference to the string, we can provide this reference to the string by dereferencing this pointer. So what happens is that string 1 will be the reference, the reference to string 1 will be returned by this append function call. And then it becomes string 1 again after completion of this portion of this longer expression in the statement. And so it will then call append again on S1, because this append, after returning, returns a reference to string S1 for which it was invoked. So now we can say append. And so the result of it, it will be string 1 modified by appending string 2 and then appending string 3. So this string will be modified 2 times. It will be appended with S2 and S3 content as a result of this chained function calls append. So this would be possible when we return this, but we dereference this so it becomes an object, and then object is good to initialize a reference to an object and return it. So this would explain why syntax like this is possible in general. So we can use the this pointer to refer to our own object at any time. So sometimes references to other objects or variables can be added to the data member list of the class. So here we have a point. Apparently this point has to do something with a graph class, which perhaps represents a portion of visible screen. And so apparently we want to make this point to be visible in this graph. And in this current design, we add a reference to the graph to the list of data members. So classes can have references as members, and a reference replaces pointer and adds design constraints that we may need. The thing is that the reference is very much like pointer, but remember it cannot be changed. Once initialized, it will stay the same at all times. So the reference has to be initialized. You cannot create a reference without initializer. And this means that whenever we have a reference to another object in our class. So for instance, if we had added some reference to this string, I don't know, it may look like this. I'm not going to hold on to this, but if I had a reference to an integer, okay, a reference which is the ampersand right here, an integer ref, something like this. then I would be required to, in every constructor of string that we have, this constructor, this constructor, this constructor, this copy constructor, everywhere, I would have to initialize this reference using initializer list like this. Okay, so I'll have to populate this reference with some kind of object, right, which would have to be provided to this constructor. So in case of a default constructor, I don't know what kind of object, but this has to be a modifiable object because this is a non-constant reference. So anyway, so we need to capture the address of some object in this reference. And my point is that every constructor must have this kind of initializer on its initializer list. This is the only place where reference initialization is permitted if you decided to add a reference as a data member to your class. So I'm not going to use any of this in our sample code, so I'll just simply remove this, just to remove my changes from these files, and I've used it only for the demonstration. And so this is why we say initializer list has to be used to initialize references if they're present in our classes. So this is an example of a point constructor, right? So this point has a specific constructor which takes three parameters: a reference to the graph object and coordinates x and y, which are integers. So right here we take all of these parameters, and what we must do is, I would prefer this version of initializer list. So basically following the order in which these member variables appear in the structure of our point class, the reference first is populated with the reference provided to the constructor, and then x and y also initialized. So this is very, very standard type of syntax. And in the latest version of the compiler, I typically use the curly braces. Curly braces, you can see that these are braces, these are not parentheses. And the earlier version of the compiler would only permit parentheses, but now using braces on the initializer list is pretty standard practice. So this is called universal initializer syntax. So again, the point here is that initializer list is the only place to be able to initialize any kind of reference that our object contains. So initializer list, and we have examples of initializer list right here in our code. Of course, initializer lists are present in constructors. So the preferred constructor syntax by most professionals is this, right? So instead of using constructor body, we want to be able to spell out everything that we can possibly initialize using the initializer list. So the idea of initializer list is pretty simple. You know that constructors are used to populate. Let me move this header file here. So we have two data members in this Java-like string. String view, which is a very nice object that that is kind of similar to Java-like string in C++. And the second is a pointer to dynamic memory if we decided that our string owns allocated dynamic memory. So, so then initializer list, as you can see, it's very uniform. In fact, I think I coded them once and then copied and pasted and copied and pasted over and over again, just modifying the current parameters. And you see that the idea is that this string view appears to be first on the initializer list, and we use the comma, and then the second data member of this class appears next on this initializer list. If I add something else to the list of the data members our class, then I would add it right here, just put a comma here and keep adding other data members to this initializer list. There are actually three types, typical types, when the initializer list has to be used. So there's no other option but to use it. With references. So if our class has references to objects, we must use initializer list to initialize our references. And therefore, constructor has to have a list of parameters providing these references. A second example is that sometimes we can have data members with no default constructors. For example, if string view object does not have default constructor, we have to choose existing constructor with appropriate parameters, and therefore we have to use initializer list entry like this and say that this object we would like to initialize with this specific parameter. So there, if string view did not have default constructor, this is the only way for us to be able to initialize it. Otherwise, it'll simply will not be able to compile our code. And finally, if any of our data members right here were made constant, for instance, if this pointer was made a constant object like this, again, I'm not going to retain this this change, because I don't think I need this really, because this is pointer to dynamic memory in itself is relatively, right now it will probably compile like this. Actually, I will even try to compile it with this change. Let me see if it compiles. Yeah, there's somewhere. Yeah, somewhere. No, this cannot be made constant. So I'm going to remove it, but for the sake of the demonstration, I'm just saying that if something is constant, that we made the data member, which we decided to make it constant so that we have to initialize it and then never change it again. Again, the initializer list is the only place to provide the initial value. So with this, I will obviously remove this from our code, not preserve this change. But these are the three instances where you just have to use constructor initializer lists. Now, also, it's just important that when you provide the value to the initializer list element, like string view and pointer to string, which are data members of Java like string right here, we could be making function calls over here, like we could call some function with some kind of parameter and whatever. Just be careful that you should expect that this entire object is not fully constructed yet, and so therefore there could be some restrictions on what this function could do. In other words, this function, if you decide to call function to initialize this object right here in our Java-like string, then you have to be extra careful not to pass this pointer to this function and expect that this object is already available for use. So of course I'm not going to retain this change, but this is what this last thing is about. And debugging could be when there's something complicated as this. Debugging session could get a little bit complicated because normally during debugging session we'd like to see the call stack of all functions that were called, and sometimes it could be a little bit obscure, like from where exactly a function was called. So just initialize the list. Again, the bottom line is that the idea of all constructors, really, this is just the bottom line and the best practice, to keep them as simple as possible. And one, actually there's even technical reason for it, is that if an exception is thrown from the constructor, the destructor is never called. It's just the way C++ standard recommends. The rule for using constructors and destructors. And so not being able to call the destructor of an object can be a little bit frustrating, and this could be really complicating design. Even for instance, if today your object is quite simple and you start doing something complicated in the constructor, tomorrow the rest of this code could get more complicated. This would give you a little bit of a headache down the line. So the bottom line is, and the best practice is, to keep constructors as simple as possible. Don't do anything that could be ending up in some kind of errors. You can always initialize the object with some simple values and later on finish configuration of your class. It's normal. Things are complicated sometimes. To be able to fully configure object, to have it properly, ready to use, it may take some time. And it's best to do it through regular member functions and keep constructors very simple, so that you really don't expect anything unexpected from your constructors, such as, for instance, exceptions or any kind of errors, exception object being thrown.